Okay, so moving on to the lateral directional controls. Of course, now we're dealing with changes in aileron and rudder angles, and primarily we use them to turn the aircraft, of course, and also sometimes to correct or trim for lateral asymmetry. So think back to our discussions about imbalances in thrust on multi-engined aircraft. For example, the engine out situation, right? We'll use the rudder to trim for that imbalance. So of course the initial response to changing the aileron or rudder deflection angles is a change in the roll or yaw rates respectively, right? That's ultimately what we want to achieve. But the long-term response is actually quite complex and very highly specific based on the aircraft because of the inherent coupling between roll and yaw. So again, think about the Dutch roll, for example, which demonstrates that if we excite the aircraft in yaw, then we also start rolling as well. So very complex dynamics here. But again, we can take a look at what happens to various parameters given a step input. This time we're dealing with aileron deflection angle, and we can see what happens in both in the initial and long-term phases for that same aircraft, the jet airliner, in the same flight condition, right? So if we make this step input to the ailerons, we showed this with the roll mode, right? Roll rate will ramp up gradually and then achieve essentially a steady roll rate. Now, of course, we have these oscillations apparent here, while all of the lateral directional forces equalize, but essentially this will converge towards a steady roll rate. And the effect of that short term is that after a certain period of time we achieve a constantly increasing bank angle, right? And in the short term, for this particular aircraft, within 10 seconds, yaw angle and pitch angle do not change, right? But of course, what we saw with the spiral mode is that if we leave that condition to develop, what happens is the aircraft starts to side slip in the direction that it rolls, and therefore we have some other dynamics as we allow that mode to develop. So namely, we continue to roll, so the roll angle continues to increase. As a result, the side slip angle starts to increase. Of course, now we've rotated our lift vector, and so our pitch angle will start to decrease because we don't have the same force applied at the static margin in order to maintain longitudinal stability. So that's why that starts to diverge. And then, of course, as we saw in the spiral mode, if it's unstable and the bank angle continues to diverge, then so does the forward speed, or the airspeed, right? So you remember in the demonstration of the spiral mode, the bank angle continues to increase, the altitude starts to reduce, and the airspeed starts to increase, and you can see that diverging here on these charts. So as you can see, there's quite a lot of trade-offs here with some of the dynamics between the angular velocities, the angles in roll, pitch and yaw, and then also in the velocity vectors as well. And this obviously demonstrates the coupling between roll and yaw if you change or make a step input to just one of the control surfaces in the lateral directional sense. Similar dynamics you would see if you made a step input to the rudder, although again, just to remind you, this the roll mode, which is essentially what we're doing here, making a step input to the ailerons, is an example of a first order response, which is different to that of the the Dutch roll and if you made a step input to the rudder, for example.